In this video, we're going to talk about limits at infinity. And what that means is we are taking a function like 3x squared all over x squared plus 1, which is a rational function, and we're looking at that function as the limit as x approaches infinity or negative infinity. There's a number of ways to do this. We can look at it graphically, we could look at it in a table of values, and we can also do that algebraically or analytically. So for example, here I know that this function, 3x squared over x squared plus 1, has a horizontal asymptote at y equals 3, and that means that graphically, as this function approaches positive infinity, it's actually going to get really close to that value of 3. So the limit as x approaches infinity is 3. Same thing going the other way towards negative infinity, it's going to edge up really close to that horizontal asymptote. So the limit as x approaches negative infinity is going to be 3 as well. And I can look at a table of values going bigger towards positive infinity here, 1, 10, 100. It's going to get close to 3, and it's going to behave in the same way as it goes towards negative infinity over here. So in that last slide, I mentioned something called a horizontal asymptote, and before we dig into all of this, I did want to remind you, for a rational function, how you find the horizontal asymptote. Now you might remember from years past where you have an n over mth degree polynomial, that's a rational function. So you take the n degree of the numerator and the m degree of the denominator and you compare them. So if the top degree is less than the bottom degree, that is a y equals 0 or the x-axis, that's your horizontal asymptote. And if n equals m, then those coefficients a and b, so y equals a over b, that's some number that's not 0, that's your horizontal asymptote. And if n is greater than m by 1, you're going to divide that top function by the bottom function, and that's going to give you an oblique or slant asymptote. If n is greater than m by more than 1, so 2 or 3, etc., then there's no horizontal or oblique asymptote. And that means in terms of limits as x approaches infinity or negative infinity, if y equals L, some number, is a horizontal asymptote, then just like in our last example, the limit as it approaches positive or negative infinity is going to be that horizontal asymptote numerical value. So there are going to be plenty of rules and plenty of examples that we go through in this video, but a nice little rule to keep in your back pocket is as the limit as x approaches infinity of some real number c over x to some positive exponent r, that's going to equal 0. And same deal for when it's x approaches negative infinity of that same function, that's also going to equal 0. And in practice, it looks something like this. So let's say I have an example where the limit is x approaches infinity of this function here, so 5 minus 2 over x squared. You can always rewrite it like this and look for the horizontal asymptote, so that's an n equals m rule, so y equals 5 over 1. That's your horizontal asymptote. You could look at it graphically as well. But the way that you could break up this limit algebraically is to split your 5 and your negative 2 over x squared into the limit as x approaches infinity of just 5 minus the limit as x approaches infinity of 2 over x squared. Now this is the rule that we were just talking about up here, so I replace that with 0. And the limit as x approaches infinity of 5, that's like y equals 5, so that's a horizontal line at 5. So that limit is 5. So 5 minus 0 gives you 5. A lot of 5s here. So if I'm actually looking at this graphically, as this function approaches infinity, it's going to edge closer and closer to 5. So that's another way that you can work with this function. Let's move on to a little bit more complex example. So I have another rational function here, 2x minus 1 over x plus 1, and I want to find the limit of that function as x approaches infinity. And if I just separate the numerator and the denominator and take the limit as x approaches infinity separately, they're both linear, positive linear functions, and they both approach positive infinity as x approaches infinity. But infinity over infinity is not a number, and that is what we call an indeterminate form. So there is a way that I can actually work with this and find a value that is not infinity over infinity. And the way that I do that is divide both the numerator and the denominator by x. because that's the highest power of our denominator. And what I end up with is 2 minus 1 over x over 1 plus 1 over x as a new function, which is equivalent to this, so I haven't changed anything. And so then I break up my limits. I have limit as x approaches infinity of 2 minus limit of x approaches infinity of 1 over x all over the limit of x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x. As that approaches 2, that's a horizontal line at 2, so that limit is 2. Same deal with this one down here, that's going to be 1. And as we learned previously, the limit as x approaches infinity of 1 over x, or a function like that, is going to be 0. So 2 minus 0 over 1 plus 0 is going to give me 2, which is also the horizontal asymptote, and graphically we can prove that as we approach positive infinity, that thing is going to edge closer and closer to 2. So now I'm going to take 3 examples and I'm going to apply my horizontal asymptote rules in terms of n and m. So let's take a look at an example where n is less than m. So that's my function 2x plus 5 over 3x squared plus 1, and that's the limit of that function as x approaches infinity. Now I'm going to divide both numerator and denominator by x squared because that's the power, or the highest degree in my denominator. So once I divide everything by x squared, I get a function that's 2 over x plus 5 over x squared, which, as the limit of x approaches infinity for both, is 0 plus 0. So that's likely to tell me my answer is going to be 0, but let's do the bottom just in case. And then that's going to give me 3 plus 1 over x squared, and that's 3 plus 0. So 0 divided by 3 is 0. And using the horizontal asymptote rule, when it's n is less than m, my horizontal asymptote is y equals 0. So that's why this whole thing is equal to 0. Now let's try this example where n is equal to m. So I've got 2x squared plus 5 over 3x squared plus 1, and let's find the limit of that function as x approaches infinity. Same deal as last time, I'm going to divide both numerator and denominator by x squared. And you can probably already guess, if you know your horizontal asymptote rules, that it probably should go to y equals 2 over 3, but let's just make sure. So once I divide everything, numerator and denominator by x squared, I get 2 plus 5 over x squared, and as I take the limit as x approaches infinity, I get 2 plus 0, and then in the denominator, I get 3 plus 1 over x squared, and as the limit of that as x approaches infinity is going to give me 3 plus 0, and lo and behold, the limit is going to equal 2/3. And now let's take an example where n is greater than m by 1, which will produce a slant or oblique asymptote, which would mean that I would need to divide my numerator by my denominator to find that. I'm not going to do that just yet because I'm going to see if I can't find the limit as x approaches infinity like I have been. So let's divide both numerator and denominator by x squared because that is the degree in my denominator. And what I end up with here is the limit as x approaches infinity of 2x plus 5 over x squared. So the thing about 2x is that's a positive line, and that is going to approach infinity as x approaches infinity. So I'm going to get infinity plus 0 in my numerator, and in the denominator I have 3 plus 1 over x squared, and that's going to become 3 plus 0 as x approaches infinity. And I have infinity over 3, and if I look at the graph of this original function in blue here, it's going to look like, hey, that thing is going to infinity. But actually the limit doesn't exist because the numerator is going to approach infinity without bound, but the denominator is going to approach 3. Those two ideas are not the same, and I can't define that as infinity, so therefore it does not exist. So here's a nice little summary of those last 3 problems. So if n is less than m, so the numerator is less than the denominator, then that means that the limit is going to be 0. If they are equal, numerator is equal to the denominator, then it's going to be y equals a over b. And if the degree of the numerator is greater than the degree of the denominator, then that limit does not exist, just like in our last example. Let's take a look at an example that's not so nice looking. Let's say I have a function that's 3x minus 2 all over the square root of the quantity of 2x squared plus 1. At first glance, that does not look like the n over m kind of rules that I've been looking at before. But I can treat it algebraically just like I looked at those other examples. So what I'm going to do here is I'm going to divide both numerator and denominator by the square root of x squared. So I'm going to divide by the square root of x squared in the denominator here because it's under a square root. I'm going to keep it the square root of x squared. But what is the square root of x squared if I simplify it? That's just x. So I'm going to divide the numerator by just x. X and the square root of x squared are the same thing. You're not changing anything. So I'm left with this quantity here. So I've got 3 minus 2 over x, and that becomes 3 minus 0. And then here I'm going to keep that under the square root, and I've got 2 plus 1 over x squared, and that becomes 2 plus 0. So that is a numerical limit value. So as the limit of x approaches infinity, this weird function is going to be 3 over the square root of 2. And now I'm actually going to find the limit of that same exact function, but it's as x approaches negative infinity. Now remember when I take the square root of a square function, so like the square root of x squared, that's positive and negative. And when I was approaching positive infinity in my last example, I just had x equals the square root of x squared because that's positive. But when you have something like this and it approaches negative infinity, you're going to want to use a negative square root of x squared for the denominator. Let's look at that. So dividing by x in the numerator and a negative square root of x squared, I end up with 3 minus 2 over x. When x approaches infinity, that's 3 plus 0. And then I'm going to keep this negative radical here, and I've got 2 plus 1 over x squared, and that becomes 2 plus 0 with a negative on the outside there. And then when I simplify it, it's just the negative of our last answer as x approaches positive infinity, but when it approaches negative infinity, it just becomes the negative of that limit. So negative 3 all over the square root of 2. And graphically, here's why. The upper horizontal asymptote is at positive 3 over rad 2, and the lower one is at negative 3 over rad 2. Now let's jump into some trig functions. Let's find the limit as x approaches infinity of just sine of x. So I always think about the graph of sine of x when I think about limits, and I know that this thing is going to oscillate between the y values of -1 all the way up to +1. And so one way to express that is with that inequality, but because it just oscillates between those two values frequently, the limit as x approaches infinity doesn't exist because it's just going to create this pattern as it goes. So it doesn't get closer to any one value. So the limit doesn't exist. So let's make that function a little bit more interesting. Let's find the limit as x approaches infinity of sine of x all over x. And so here's what I've already established, that sine of x oscillates between -1 and 1 inclusive. Now, the difference here is that I'm dividing that function by x, so I'm going to divide this inequality by x. So now I'm going to take the limit as x approaches infinity of this function, so -1 over x, and this function, 1 over x. And we happen to know those rules, and that's going to be 0 for both. So that means that the in-between here, the limit as x approaches infinity of sine of x all over x, that's also going to be 0. And graphically, if I was to look at that function, sine of x over x, it actually oscillates, but it gets smaller and smaller and smaller and smaller and smaller until it actually, the limit approaches 0 at infinity, or towards infinity. Can't count to infinity. Now let's throw in a word problem, because why not? So let's say I have this function, f of t, that's t squared minus t plus 1 all over t squared plus 1. That is the measure of the level of oxygen in a pond, where f of t equals 1 is the normal, unpolluted level, and the time t is measured in weeks. When t equals 0, organic waste is dumped into the pond, and the waste material oxidizes, and the level of oxygen in the pond is that function there. So if I was looking for the percent of normal level of oxygen at 1 week, 2 weeks, 10 weeks, as t approaches infinity, so for all of time, all you really have to do is take that function and plug in 1, 2, and 10 for these first 3 questions, and the book actually works it out beautifully. So when I plug in 1 for 1 week, it's 50% levels of oxygen. At 2 weeks, 60%, and at 10, it's about 90.1%. And now what about as the limit of t approaches infinity? So that is a function that we can very well deal with. I'm going to divide everything by t squared because that's the degree in the denominator. So this is my new numerator in my denominator. So that's going to become 1 minus 0 plus 0 all over 1 plus 0. So that's 1, or 100%. So that means that the level of oxygen in a pond approaches the normal level of 1, or 100%, as time in weeks approaches infinity. And last but not least, we're going to talk about infinite limits at infinity. And here's a very formal definition, but essentially we're working with polynomial functions that approach infinity or negative infinity in either direction. It really has to do with end behavior. So let's take a look at a few examples. So let's look at the very classic cubic function, f of x equals x cubed, and let's take the limit as x approaches infinity and x approaches negative infinity. Now, honestly, graphically, you could look at this and just tell me what these are going to be. So we'll say that as x approaches infinity for x cubed, the limit is going to be infinity because this thing is just going to keep increasing without bound. It's an infinite limit. It's a polynomial. And then in the other direction, towards negative infinity, it's actually going to approach negative infinity going that way. So easy enough for a simple polynomial. And here's another one. Although it's not a polynomial, this is a rational function, and it's an n is greater than m by 1 situation, so I have an oblique asymptote. So when I divide 2x squared minus 4x by x plus 1, I get the oblique asymptote as y equals 2x minus 6. Now, as x approaches infinity, I can look at this graphically, because this is towards infinity, so if I go up, 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 that thing's going to edge towards infinity. And so I can say that limit will be infinity. And as it approaches negative infinity, it's going to go down, 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 down. So that one is actually going to approach negative infinity as well. And so the reason that this function behaves like the last function, x cubed, is because of this oblique or slant asymptote y equals 2x minus 6. So if we just look at the behavior as x approaches infinity and negative infinity of a positively sloped line, so as x approaches infinity, that line's going to approach infinity. And as it approaches negative infinity, that limit will be negative infinity as well. That's going to do it for this video. Thanks for watching.